Hello everyone. It is 5 minutes past 6 and nobody has joined till now the session. So I am assuming that all of you will be watching this session online through YouTube and I am continuing this session. So if you remember, we had solved the first problem of calculating the equivalent stiffness. Then we had the second problem with the cart being dragged on a rough road, which turned out to be a base excitation of a spring mass system. Then we had the third part, which is a usual spring mass system. The fourth problem is actually I had left it for you to explore it last week. And the fifth problem was the standard linear fluid model. The standard linear solid model is actually described in the discussed in the class, and the derivation of expression included. So in the tutorial session, we actually did the standard linear fluid model derivation just so that the methodology is more clarified to you. And now uh, there are two more questions added for this week. So you can pause the video and see if you can do them. This is the fourth question, which was actually all these materials are available on the Drive link. There is a Drive link on the course webpage, and you can access the questions as well as the solutions there. So moving on, this was the fourth question. Actually, if you remember the class lectures, uh, there was this figure of merit calculation. What we used to do was we used the calculations to actually determine which type of material is more suitable for a specific problem. In that, we used a beam type of loading and we modeled the spring mass system using the beam spring stiffness. Right now, we are using the viscoelastic element as a bar. So this time, we will calculate the figure of merit if it is a bar type of element. So using the bar type of element, what we say is, considering the same system obtained in question 3, which is the usual spring mass system, and a rod of specified mass and rectangular cross section width B and thickness H has to be designed. The length and width of bar are specified, but the height of the bar is left variable. It can be any value, lower side or higher side. Determine the figure of merit for selecting the bar material so that the maximum amplitude of displacement is minimized or minimum under the harmonic loading. So first of all, what we'll do is we'll draw the schematic for the problem. So sorry, if we remember, the question 3 had a system of this equipment being mounted on a cart and the cart was stationary. So this is K, this is M. So it is a usual spring mass system. And this is the original system. But what we are expected to do in this particular problem is we are given the same mass M, identical stiffness K, but a rod type of viscoelastic mounting or the structural damper with the loss factor of eta. So for this type of vibration based model, we know that the equation of motion is mx double dot uh, plus c structural x dot plus kx equal to f. This was f sine omega t, or in complex form we can write f e raised to power j omega t. It is better if we write f naught e raised to power j omega t. If we non-dimensionalize this, CST is nothing but h by omega, and h is the hysteresis constant. So if you refer to the class lectures, the non-dimensional form actually can be written as x double dot plus eta x dot, actually eta by omega x dot plus kx equal to f by k e raised to power j omega t. So if we substitute small x as capital X e raised to power j omega t, this is all discussed in class. So nothing to worry about. And we make all the substitutions. This magnitude of x is basically equal to magnitude of f naught upon k, and in denominator we get 1 minus omega square whole square plus eta square total to the power of 1 by 2. So until this point, it is discussed in class. So we'll continue the derivation, or we'll continue the analysis from here onwards. So for this system, actually, this is a usual spring mass system. When the amplitude will be maximum, it is expected that the maximum amplitude will occur when this excitation frequency approaches natural frequency omega n, which is nothing but square root of k by m. So if omega is equal to omega n, then capital omega, which is the ratio of omega by omega n, is equal to 1. Then this mod of x value becomes mod of f naught by k upon 1 minus 1 square whole square plus eta square whole to the power of 1 by 2. Now this becomes 0. This total term 1 minus 1 square is 1 minus 1, which is 0. 0 square is again 0. So mod of f naught by k upon eta square 1 by 2, which is in turn mod of f naught by k into eta mod of x. So now we have an expression mod of x, sorry, mod of x is nothing but mod of f naught upon eta k. Now we have a linear bar, right? So for a linear bar, like this bar, if this end is fixed and this end is applied with a force, here we'll say F1, and the extension at this point is x. So as per this Hooke's law, the linear Hooke's law, we are assuming that the spring material is purely elastic, linear elastic. So it will become sigma equal to E epsilon. If the cross section area is A, then sigma is nothing but F1 upon A, and E is the elastic modulus, epsilon is this extension, I would better say delta L, and the length of this rod is capital L. So this is delta L upon L. So if I write it as in this form, this becomes EA by L delta L. Now we are using this as a spring element, right? So in this case, the elastic component, which is assumed to be of this form, The elastic component gives the stiffness as force is equal to stiffness into extension. So K equivalent is equal to EA by L. So we can write this K as mod of F naught upon eta E A by L, right? So this is the expression for mod of X. Now this mod of X to be minimized. This mod of X is to be minimized. So for this minimization, what we want to do is we want to maximize the denominator. The denominator here, if this is maximized, this value will be minimized. So again, what we want to do is eta into EA upon L to be maximized. So moving on, eta into EA upon L. Now we know A, right? We have a given cross section. If we remember, the width is B, thickness is H. So A is nothing but the cross section area, which is B into H. Eta E B H upon L. Now there is one more thing to note. Just a minute. Okay, nothing to worry about. Hmm. So one more thing is mass is constant. So mass is nothing but density of that material into B H L, width, thickness, length. This is the volume into density is equal to mass. Now L is variable, right? M by BH is constant. So rho into L is also constant. This implies that L is inversely proportional to rho. So eta EA by L is proportional to eta E by L. We are omitting B and H because they are constant for our design. And now L is inversely proportional to rho. So eta EA by L is actually proportional to eta E rho. Now this is variable, this is variable, this is variable. But this total variable decides the magnitude. So mod of X is equal to F naught upon eta EA by L. So now we can say that mod of X is inversely proportional to eta E rho. This is the final expression. So now we can comfortably say that we have to select a material which has a loss factor, elasticity and density multiplied as a maximum value. We have to maximize this denominator. So if some material has a very low density and a very high loss factor, but another material has intermediate density and intermediate loss factor, the intermediate one will be more preferable. We have to take all these three factors in a combined form. And as you would have seen in the class exercise, actually, uh, in the class exercise, there is a different expression we obtain But turns out that if we look for just one factor among these three, then the result may predict some other material, which is not the best material we would like to choose. So we have to take all these three material, we have to consider all these three factor of that material simultaneously, and then we have to decide if that material is better or not. So just try it by yourself. There is a class example on beam stiffness, and this example was on bar stiffness. And based on that, if you still have doubts, you can discuss it on the discussion forum on NPTEL. So now we have a new question. So in this, this is the usual spring mass damper system. So find the expression for excitation of a spring mass damper system for a general periodic excitation using Fourier transform, and use it for the solution for any general forcing. So why is this problem even relevant in the course? So in the course right now, what we study is, okay, so we have one participant here, Venu Srinivas, and we'll continue. Okay, so you heard the question, Venu?
No, sorry.
Okay, no issue. So this is the question we are discussing right now. What we do is we have the spring mass system, mass, stiffness, and damping. All three are there. The upward direction is taken as positive x, and upward is also the force which we take as positive. So we have to find the expression for any periodic excitation and use Fourier transform to form the solution. Like if we remember the class lectures or the usual solution approach, what we usually have is we usually find the solution for M. This is K. This is C. If we assume X in this direction and F in this direction, so what we assume is F is of the form of F naught e raised to power j omega t, or basically it has only one frequency component, and that also of a sinusoidal or cosine form, sinusoidal basically. So what we assume is with, sorry, with time, the variation of f is like this, right? And then we write mx double dot plus cx dot plus kx equal to f naught e raised to power j omega t. So what we do is we keep the x as x naught e raised to power j omega t. We substitute it here, and finally we get minus m omega square plus c omega plus k j c omega. And we have this capital X naught e raised to power j omega t is equal to f naught e raised to power j omega t. And then we have x naught equal to f naught upon k minus omega square m plus j c omega, which is later simplified as f naught by k upon 1 minus capital omega square plus j of 2 zeta omega. Sorry. So this is the usual solution when you have only one frequency component. But what if the force is like a rectangular wave? If this type of variation is there, it is also a periodic force. Or we have a triangular forcing like this, or any type of forcing for that matter. Like there are multiple types of forces, and remember, this method is actually more efficient if the forcing is periodic. So we will assume that it is not sinusoidal, but it has a particular repetition and it corresponds to time period t. So therefore, what we are going to do is we are going to find a solution for this periodic forcing. So what we assume is mx double dot plus cx dot plus kx is equal to function of time f of t, and such that f of t is equal to f of t plus capital T. So this capital T is the time period of that force. So another thing is, if you can directly take it as linear differential equation. It is a linear equation. What I mean by linear equation is, if x1 is one solution of equation 1, we'll call it as equation 1, and x2 is another solution of equation 1, then x equal to alpha x1 plus beta x2. We are assuming that x1 and x2 are different functions, linearly independent functions are independent. So then this linear combination, by taking alpha and beta as constant, this is also a solution of the above equation. Do you guys need me to prove it, or you can accept the result?
No, continue.
Okay, so that means that if we have f decomposed as f1 plus f2 plus f3 and so on up to fn, then we can have mx double dot plus cx dot plus kx equal to f, which can be decomposed as mx1 double dot plus cx1 double x1 dot plus kx1 equal to f1, mx2 double dot plus cx2 dot plus kx2 equal to f2, and so on up to mxn double dot plus cxn dot plus kxn equal to fn. If we add, sorry, if we add these equations, then it will form m of x1 plus x2 plus dot 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 up to xn double dot plus c of x1 dot plus x2 dot plus dot 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 xn dot plus k of x1 plus x2 dot 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 xn equal to f1 plus f2 dot 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 fn. That means mx double dot plus cx dot plus kx equal to f has a complete solution as x equal to x1 plus x2 plus up to xn. So if we solve for individual small f, we can actually get the solution, the complete solution. And the other thing is, we know that the sinusoidal function has a direct solution. We can obtain the solution directly. So what we will try here to what we will try to do here is we'll decompose f as a sum of harmonics, sum of sinusoidal functions. So that is done using Fourier transform. So if we write it in the complete complex form, it is written as n equal to minus capital N to capital N Cn e raised to power j omega n t. But if we write it in real form, it is usually written as ft equal to a naught by 2 plus summation of n equal to 1 to capital N an cos of n omega t plus bn sine of n omega t. Now, omega is basically 2 pi by t, where t is the time period of f. So we'll move forward. Uh, Here we will directly use the results from Fourier series expansion. So this Fourier series expansion shows that these the constants a naught, an, and bn, they can be directly found as a naught is equal to 2 by t integral of minus t by 2 to t by 2 f of t dt. An is 1 by t integral minus t by 2 to t by 2 f of t cos of n omega t dt, and bn is 1 by t minus t by 2 to t by 2 f of t sine of n omega t dt. Sorry. These three things can be used to finally get the values, the solution. So usually in a harmonic forcing, we what the forcing is usually given, a naught value comes out to be 0, or a naught value wherever it is present, it will just shift the mean position. So that is not much to worry about. But the harmonic components we have to actually check. So I leave it to you as an exercise to find Cn values as a function of An and Bn. So Cn and C minus n, they come as complex conjugates with one as An plus JBn and the other one as An minus JBn. So you can find it yourself. And finally, what we do is we take mx double dot plus cx dot plus kx equal to summation n equal to uh, Actually, we can ignore the negative part, assuming that we will take the real part or the complex part only, because the minus n and n factor will actually result in Cn plus C of minus n something something expression, and it will result in sine and cos terms. So what we usually do is we use a much simpler approach using n equal to 0 to capital N, sorry, with Cn as e raised to power j n omega t. So now what we do is we use m xn double dot plus c xn dot plus k xn equal to cn e raised to power j n omega t. Now we can find capital Xn as cn e raised to power j n omega t upon k minus m and n omega square plus j of c n omega as capital Xn. And we have this whole series, right? So x is basically summation of xn e raised to power j n omega t, where n is from 0 to capital N. This capital N can approach to infinity, but we only take finite values depending on how much the contribution of the forcing is in those particular modes. Now, if there is no damping, the expression becomes much simple. Like we have this Cn e raised to power j n omega t upon k minus m of n square omega square. So now we can actually, we don't have the complex part, so there is no need for vector addition or something. The upper part can be taken care of, but the lower part is kind of a series expansion, and the analysis becomes much easier. So in that sense, we can actually get the final amplitude. So this is the final amplitude we get after summation. And when we usually do the experiment, what happens actually, uh, we use this to find the natural frequencies of a continuous system. So what we do is, like, if this is a system M, this is K and C, and we apply a delta impulse force, delta T minus T naught, which means, and magnitude is F naught, which means that there is a F naught magnitude of impulse provided during T equal to T naught. So delta function is basically, it is zero everywhere except T equal to T naught. Here it is infinitely large, such that the integral or the total impulse change across this is actually equal to F naught. F naught is equal to m of x at t positive minus x of t negative. So in that case, actually, if we take the Fourier transform, the an and bn values actually become 1. Actually, one of them becomes 0, one of them becomes 1, depending on whatever happens. So actually what happens is we get a like uniform spectral signal. What is meant by the uniform spectral signal is that all the frequency components are present. So now if equal amplitude of all frequency components is present, what will happen is the final response will be according to the magnification factor. And if we assume that the damping factor is much smaller, like C is negligible, so then if you remember the this magnification factor graph goes like this. This is capital X, this is omega by omega n, and this is 1. So actually maximum magnification will happen near omega n. For this case, maximum magnification will happen. So after some time, all the remaining frequencies will die out and only the frequencies corresponding to the natural frequency will remain. So if the system is not like a simple spring mass system, but a continuous system, like it is a beam, then it has a magnification factor graph like this. This is at omega 1, this is omega 2, omega 3, omega 4, and this is omega, this is capital X. It is the modal amplitude. So only these frequencies will show a distinct peak if given a specific impulse. So this analysis can be used for any type of forcing, but there are more better ways actually, like convolution integral and all, to actually solve for non-periodic type of forcing. So that is out of the scope for this particular course content until this week. Maybe it is covered in next week, maybe not. So then we move on to the last question. So the next question says that find the damping of spring mass system to result a maximum transmissibility less than 2 for any frequency of excitation, and find the displacement transmissibility of the system at frequency ratio zero point 0.2 and 20. So what is the percentage change in transmissibility in these regions with respect to the undamped case basically? So we'll go to the problem. So this is the problem. We have this mass, we have the stiffness K, damping C, and in non-dimensional terms we can write that capital omega is basically the excitation frequency over natural frequency, xi is or zeta is basically damping coefficient over critical damping coefficient, which is C by 2 root km, and using that we can write the displacement transmissibility, capital T, as square root of 1 plus 2 xi omega square upon 1 minus omega square square plus 2 xi omega square. So this is our formula which has been derived in the class lecture. So what we are expecting here is the maximum transmissibility attained in a cycle or for a system should be equal to 2, actually less than equal to 2. So what we are expecting here is maximum transmissibility occurs at resonance, that we know. So what we expect here is for omega equal to 1, that is resonance. T is basically square root of 1 plus 2 xi omega whole square upon 1 minus omega square. Actually, we'll substitute omega equal to 1 here. So that will give us 2 xi square upon this omega equal to 1 gives this as 0, so this becomes 2 xi squared. We can write it as 1 plus 1 by 4 xi square. So this is at resonance. Now t should be less than equal to 2. So we take a square on both sides. 1 plus 1 by 4 xi square is less than equal to 4. So this can be better written as 3 is less than equal to 1 by, actually it should be written like mm, 1 plus 1 by 4 xi square is less than equal to 2 is less than equal to minus of 1 plus 1 by 4 xi square, because it is a plus minus. So then this inequality will actually be much easier, but this is the one we want to solve. We can use equality first. 1 plus xi, sorry, 1 plus 1 by 4 xi square plus minus equal to 4, and 1 plus 1 by 4 xi square equal to minus plus 4. So 1 by 4 xi square equal to minus plus 4 minus 1. This becomes minus 5 or 3. So damping square cannot be negative value, so we cancel this. So we use xi square is equal to 1 by 12, or xi is equal to 1 by root 12. So this is actually the value of damping we require, so that the maximum transmissibility is less than or equal to 2. For this, xi should be greater than equal to 1 by root 12. So you can check it by substitution also. So now that we know this thing, we move forward to the other parts. So this says that if the frequency ratio is near zero point 0.2 and 20, what is the percentage change in these regions? And what is actually the transmissibility in these regions? So first of all, if xi was equal to 0, if xi was equal to 0, this would have been infinite. So for capital omega equal to 1, T initial would have been up to infinite. T final after adding damping is at max 2. So the ratio for omega equal to 1 is equal to Tf upon Ti, which is 2 by infinite, that comes out to be 0. So it is a infinite times improvement, or the transmissibility is reduced to, with respect to infinite, any finite value is 0. So this is good. The resonance failure is avoided. But if we talk about the other regions, like if capital omega or the frequency ratio is zero point 0.2, so then what is the formula of transmissibility? Square root of 1 plus 2 xi omega whole square upon 1 minus omega square whole square plus 2 xi, sorry, omega whole square. And if we substitute zero point 0.2 for omega equal to 0.2 and xi equal to 1 by root 12, what we get is we get the transmissibility equal to 1.0417. So actually the transmissibility is greater than 1. This is usually the case for stiffness dominated region. Transmissibility is 1 for perfectly rigid one, keeps on increasing until resonance and then decreases. But if there was no damping, actually, sorry, it is 1.0411. Now, if there was no damping, this would have been, this is TF, TI would have been square root of 1 minus 1 omega square whole square, which is basically 1 upon mod of 1 minus omega square. It would have been 1.0417. So there is marginal improvement, like this is TFTI. So actually, there is a minor decrease in transmissibility by addition of damping, but it is not significant. And that makes sense actually, because addition of damping does not actually change the amplitude of vibration much significantly in the stiffness dominated region. This frequency ratio of zero point 0.2 signifies the stiffness dominated region. So by that sense, we can say up to some extent that transmissibility is okay. But remember, transmissibility does not equate with the amplitude of vibration. Transmissibility is basically the ratio of vibration. Like if the base is exciting at x1 and the mass is exciting at x2, so x2 upon x1 is basically the transmissibility, how much vibration is transmitted to the body. So if we go for omega equal to 20, this is basically the inertia dominated region. So if we go for omega equal to 20, the TF is basically 1 plus 2 xi omega whole square upon 1 minus omega square whole squared plus 2 xi omega whole squared, and Ti is nothing but 1 upon mod of 1 minus omega square. So TF comes out to be 0.029 and Ti is 0.0025. I'm not calculating them here. You can do it on your own. I have written the formulas here. So now here is one interesting thing. So if you see, the transmissibility in the inertia dominated region is actually increasing with addition of damping. So this is one very important thing to notice here. So if you are working in inertia dominated region, then to reduce transmissibility, it is a very bad idea to add damping. It will actually increase the transmissibility. So if we see on a graph, and this red line shows TF, which is the, sorry, TI, which is the undamped case. So the transmissibility increases up to infinite and then goes down very sharply. This is omega n, sorry, this is omega n, this is t equal to 1. But if we add damping, this shows TF or the damped case. So we saw in a stiffness dominated region, it shows a minor improvement. It shows an excellent improvement here, but it actually shows a negative improvement in this region. So If we talk about this region, sorry, if we talk about this region, or basically whatever is to this side, here actually the TF is greater than TI, such that the transmissibility actually increases. And if we are in this region, transmissibility decreases before this point. And if we keep on adding damping, like for infinite damping means whatever the structure is given disturbance, the damper just does not allow it to dissipate energy. So it behaves more like a rigid case. If damping is tending to infinite, we'll just look into a case like T is basically square root of 1 plus 2 xi omega whole square upon 1 minus omega square plus 2 xi omega whole square. So, sorry. If damping is tending to infinite, what will happen is 1 by 2 xi omega whole square plus 1 upon 1 minus omega square by 2 xi omega whole square plus 1. Now xi is tending to infinite. Sorry. So this goes to 0. This goes to 0. T is nearly equal to 1. So the whole force is exactly transmitted to the solid structure. So having too much large of a damping is also very harmful. It does not help in inertia dominated region. It will definitely reduce the effects in the stiffness or resonance dominated regions, but it will actually have a negative impact or a counter impact in the inertia dominated region. So in inertia dominated region, if you want a very low transmissibility ratio, it is advisable to have a very low damping factor. So I think that is sufficient as a discussion. So all these lectures will be added to to the NPTEL platform. There is a separate link there provided for that Excel sheet. In that Excel sheet, you can see the folder which contains all these PDFs, the question PDF, the associated solution PDF, and the links for video, the YouTube links for videos. So you can access it and do try the quizzes. So I think that provides sufficient closure to this week. Just as a mild exercise, I would suggest you that there you try one of the cases like you remember this question, right? For this periodic excitation, I just want you to try for a sorry. I just want you to try for a rectangular wave. I'll just use a black pen. If it is a rectangular wave with the amplitude of f naught, time period of t, omega is equal to 2 pi by t, we can use it directly. And this ratio is actually equal. This is t by 2, this is t by 2. So there are cases where this is actually called the duty cycle. This length to the total length is called duty cycle. This equal refers to 50% duty cycle. So we are assuming that it always remains 50%. There are cases where it changes from 0 to 100. 100 is basically a step function, and this is actually, we are assuming it is a 50% duty cycle thing. So I just want you to explore what will happen in this case. There is a Fourier expansion. You can use the direct expression for Fourier expansion available. You can use online or you can see any book. It is easily available. And the same way you can obtain for rectangular wave or other, but the triangular wave and other forms. But this is the most standard one. So I would like you to try this.
Yeah, just a generic question. Where could we see this kind of response?
This one.
Yep.
This one is most usual one if you see a, like, if you are dragging this mass, right? There is a support structure, there is an elastic beam, and there is friction. Like whenever you are moving this side, this structure experiences a this type of the this side of force, which is equal to Fc. And if it is moving to the opposite side, if it is moving to this side, this force is Fc, right? So this
Yes.
magnitude of Fc never changes. But if there is an elastic linkage between the driving member and this mass, there is a spring mass system which will be equivalent to this system, and this F will be equivalent to this rectangular waveform. You are getting the point?
Yes.
So in those cases, we can see this one. Then there is this triangular and step waveform. There is actually the Amazon guys or the any packaging agency. They actually model the impact one, the impact response. So what they do is they have this packaging thing. So they analyze it for how much damping or how much packaging, how much stiffness and other parameters should be optimized such that the package experiences a below critical limit of acceleration so that the internal components of that package are not damaged. So what they model it for, if it drops from a height h onto the floor, if this is height capital H, so the velocity u naught will be rho square root of 2gh. And when it impacts here, if we assume it is a purely a plastic collision, then mu naught is basically the impulse. And if we assume elastic collision, then 2 mu naught. So because after elastic collision, it will be u naught upwards. So this is the impulse. So they model for these type of particular scenario. So the impulse function, rectangular function, and many other types of forcing are usually seen everywhere. The sinusoidal one is actually the most easy to solve. That is why people use it in the introductory courses. But in very complex scenario, it is hardly just one sinusoidal function. It can be combination of two or three sinusoidal. It can be a special waveform. It can be impact. It can be any other.
Okay, got it. Hmm.
Thank you.
Thank you. This explanation was good.
So we can stop this session now, right?
Yeah.
Okay. Thank you.
Thank you, Karo.